These are the answers to the practice quiz on the periodic table and chemical bonding. Number 1. In an early version of Mendeleev's periodic table from 1871, an element with a mass of 68 did not have an element symbol listed next to it, but a dash instead. Which of the following represents the most likely explanation for this situation? So let's take a look at an early version of the periodic table from Mendeleev. And let's focus on this section, and we can see the elements boron, carbon, nitrogen, and oxygen. And then underneath those elements on the periodic table would be aluminum, silicon, phosphorus, and sulfur. Now on Mendeleev's periodic table, you see those two question marks next to atomic masses 68 and 70. So what's underneath aluminum had not been discovered yet, and eventually was named gallium when it was discovered and had properties similar to those that Mendeleev had predicted. In a similar way, there's an element underneath silicon that has an atomic mass of 70, and that was eventually discovered as the element germanium, again with properties similar to those predicted by Mendeleev. So the correct answer to this question is B. Mendeleev predicted the existence of this element and that it should be located below aluminum, and this element was unknown in 1871 but is known as gallium today. Number 2. Which of the following is the best reason to justify why two different elements should be located in the same group or family? So choice A says the elements are both classified as nonmetals and exist as gases at room temperature. Here in this section of the periodic table, we see that both nitrogen and oxygen are nonmetals. They are both gases in the air, but they are not in the same group or family. Choice B says the valence electrons of each element are located in s orbital. In this portion of the periodic table, hydrogen, lithium, beryllium, sodium, magnesium, potassium, calcium, rubidium, and strontium, they all have their outermost valence electrons located in an s orbital. And again, they're not all in the same group or family. Now, lots of these elements, lots of metals, can react with oxygen to form an ionic compound. That's not specific enough. So the correct answer is D. The fact that each element has the same number of valence electrons in their outermost energy level, that is the criterion for why two different elements should belong in the same group. Number 3, we have two formulas listed. We have BF3 and CO2, and we have to determine which of the following chemical formulas is most likely to be correct based on the rule that elements located in the same group should react in similar ways and in the same proportions with other elements. So let's take a look at a section of the periodic table that includes boron, carbon, nitrogen, oxygen, and fluorine. And if we start with BF3, we could replace boron with aluminum. We could replace aluminum with gallium and still have 3 fluorine atoms bonded to that element. If we decide to hold the boron fixed, we could change fluorine to chlorine, or we could change chlorine to bromine, and again, all of these would be formed by substituting one element for another. I could also replace both boron and fluorine with elements in the same family, and I would get something like aluminum and 3 chlorines, but still the same 1:3 ratio. In a similar way, I could replace carbon with silicon. I could replace silicon with germanium. I could replace oxygen with sulfur or selenium. And I would have all of these compounds that would be represented by substituting one element for another in the same family. So based on these choices and the pattern that we see, the correct answer is A. The problem with B is that there's not a 1:3 ratio between aluminum and fluorine. The problem with C is that there is not a 1:2 ratio between silicon and oxygen. And the problem with D is that they've substituted fluorine for oxygen, but those are not located in the same family. Again, correct answer is A. Number 4, which of the following information best justifies the fact that the average atomic mass of argon is slightly greater than the average atomic mass of potassium? So if we find these elements on the periodic table, we see that argon has 18 protons and potassium has 19 protons. So since potassium has more protons than argon, and yet it actually weighs less, we've got to find which of the following statements best justifies this. So we can eliminate choice C because argon should have fewer protons than potassium. We can eliminate choices A and B because even though potassium does have more protons, that doesn't explain why it actually weighs less. So we're looking for a reason why argon weighs a little bit more. Correct answer is D. The most common isotopes of argon must have more neutrons than the most common isotopes of potassium. Question 5 deals with atomic radius. Let's take a look at the general trends in atomic radius on the periodic table. From left to right across a period, atomic radius decreases. And from top to bottom down a group, atomic radius increases. Our first choice says that neon should be larger than lithium. Now both lithium and neon are located in the same period, but lithium should in fact be larger than neon. So choice A is incorrect. For nitrogen and phosphorus, they are located in the same group, but phosphorus should be larger than nitrogen. So choice B is incorrect. Potassium and rubidium are also located in the same group, but rubidium should be larger than potassium. So correct answer is C. Calcium and gallium, which are in the same period, calcium should be larger than gallium because it is further to the left and size decreases from left to right. Number 6, as you move across a period from left to right, the atomic radius tends to decrease. So the answer is either A or B. Remember that ionization energy, that trend is opposite to the trend in atomic radius. So while the atomic radius does decrease from left to right, it's because the electrons are being pulled in more tightly. Ionization energy would actually increase from left to right. So the correct answer is not A, but rather B. It's because the electrons are pulled more strongly toward the nucleus because of the increasing number of protons in the nucleus. In number 7, as you move down a group from top to bottom, the atomic radius tends to increase. So the answer is either C or D. But in terms of the reason why, it's because we are changing energy levels. It's not about repulsions. It's about switching to the next higher energy level, which is located farther away from the nucleus. Number 8, we have 4 elements, potassium and rubidium, which are on the left in the same group, and we have bromine and iodine, which are on the right in the same group. So based on the trend in atomic radius, rubidium should be the largest and bromine should be the smallest. So the correct answer is either B or C. Again, there is an inverse relationship between atomic radius and ionization energy. So rubidium would actually have the smallest value for ionization energy. Bromine, having the smallest radius, should have the largest value for ionization energy because it should require more energy to pull off the electron if it is being held more tightly by a smaller atom. For questions 9 and 10, we're going to consider this diagram, which shows 2 atoms, A and B, and A has a larger atomic radius than B. If these elements are located in the halogen family, then fluorine is the most reactive halogen because electrons are being pulled more tightly toward the fluorine atom compared to chlorine, bromine, or iodine. So in choice A, it says the reaction between this mystery element A and a metal like sodium should be more vigorous. That's incorrect. The smaller the halogen, the more reactive it is. Choice B says that element A should have a greater number of valence electrons than element B, but if they're in the same family, they would all have the same number of valence electrons. And since a larger atom would be further down on the periodic table, it would have more protons. That eliminates choice D. Correct answer goes back to that inverse relationship between atomic radius and ionization energy. So the ionization energy of element A is less than that of element B because electrons are more easily removed from element A due to its larger size. Now number 10, we have the same diagram, but now we're focusing on the alkali metal family. The most reactive member of that family would be cesium. So choice A says that the reaction between element A and water should be more vigorous than the reaction between element B and water. That is true. We can eliminate choice B because A would be further down on the periodic table, be larger in size, and would have a greater atomic mass. The ionization energy of element A should be less than that of element B because it is larger and electrons are easier to remove. And these elements would lose the same number of electrons to form stable ions because they are both in the same family. Again, correct answer is A. Number 11 is talking about what happens to the size of an aluminum atom when it turns into an ion with a charge of +3. You should know that forming a +3 ion involves losing electrons, so the correct answer is either A or B. Here are some examples of atoms. We have sodium, magnesium, aluminum, sulfur, and chlorine, and we have the corresponding size of the ion. Notice that sodium, magnesium, and aluminum, their size has decreased when they form positive ions by losing electrons. Sulfur and chlorine, their sizes have increased when they form negative ions by gaining electrons. So again, the size of an atom decreases when it loses electrons. Its size increases when it gains electrons. So correct answer for aluminum is that the size will decrease because aluminum is losing electrons. In number 12, initially you might think that Cl-, the chloride ion, which is going to have 18 electrons, you might think it's the same size as the potassium +1 ion, which also has 18 electrons. But as you can see in this diagram, when chlorine gains an electron, it has a size of 1.67. The units there are in angstroms, so 1.67 angstroms. And the potassium ion is a little bit smaller at 1.52. So why is this? If they both have the same number of electrons, why aren't they the same size? It's because potassium still has 19 protons in its nucleus, whereas chlorine has only 17 protons in its nucleus. More protons exerts a larger, a stronger pull on the electron cloud. So the correct answer is B. The potassium ion should have a smaller ionic radius because it has more protons. In number 13, we're going to fill in the chart with the missing information. Here on the periodic table, if we find fluorine, it has a total of 9 electrons. The electron configuration for fluorine is 1s2, 2s2, and 2p5. You could abbreviate that by putting helium in brackets and then writing 2s2, 2p5, but that's not really much of an abbreviation. So I just wrote 1s2, 2s2, 2p5. It is located in the halogen family, and there are 7 valence electrons. It is a non-metal. The next element, we don't know the symbol, but we know it's got krypton 5s1. So on the periodic table, krypton has 36 electrons. this element has one more than krypton, so it must be rubidium with 37 electrons, and its configuration is krypton 5s1. So Rb is the symbol for this element. It is a member of the alkali metal family. It is in group 1 and has one valence electron, and it's a metal. Our next element has argon 4s2, 3d10, and 4p6. Now argon is a noble gas. That's 18 electrons. If we add plus 2 plus 10 plus 6, that means we're adding 18 electrons to what argon already has. That's a total of 36 electrons. So this electron configuration represents the element krypton, Kr. It is a noble gas. It has 8 valence electrons, and it is a nonmetal. Finally, silicon, which has 14 valence electrons. The configuration for silicon would be 1s2, 2s2, 2p6, or you could just write neon in brackets, and then followed by 3s2, and then finally 3p2. So that electron configuration for silicon, it has 4 valence electrons, and it is a semi-metal or a metalloid. In number 14, for each of the following pairs of atoms or ions, circle the one that has the larger radius. Starting with the general trend in atomic radius, if we can find two elements in the same group, like nitrogen and phosphorus, the one that's further down the group should be larger in size. So phosphorus is larger than nitrogen. And if we find two elements in the same period, the one further to the left would be larger. So between aluminum and chlorine, aluminum should be larger in size. They're in the same period. Now, based on our next choices, remember that the size of an atom decreases when it loses electrons and increases when it gains electrons. Sodium should be larger than the sodium plus ion, which is formed by losing one electron. Fluorine -1 should be larger than fluorine atom because it gains one electron. Our next two choices have ions. In the case of magnesium and oxygen, those ions actually have the same number of electrons. They're both 10 electrons. But we know from the previous question that they're not going to have the same size. Whoever has more protons is smaller. So in this situation, magnesium 2+ has 12 protons, whereas oxygen 2- has only 8 protons. Magnesium 2+ should be smaller, so we'll circle O2- as the larger radius. Now finally, for this choice, we have aluminum 3+, which has 10 electrons, but chlorine- has 18 electrons. Therefore, the chloride ion with 18 electrons is larger than the aluminum ion, which has only 10. In number 15, we have to circle the word that makes each sentence correct. Lithium and potassium are located in the same group. Reactivity for these metals increases as you go from top to bottom. So potassium will react more vigorously with water, and one of the reasons for this observation is that potassium has a lower value for its ionization energy. Now you could have circled lithium and higher, and that would have also been correct. It is much easier for potassium to lose electrons, which is why it is more reactive. Now looking at the nonmetals, fluorine and bromine are also located in the same group, but the smaller the atom is, the more reactive it is for the nonmetals. So fluorine is actually going to react more vigorously with aluminum, and one of the reasons for this is that fluorine has a stronger attraction for gaining electrons. Again, you could have said that bromine has a weaker attraction. That would have been correct as well. Fluorine has a higher value for its ionization energy because it is more difficult for fluorine to lose electrons. It's hanging on to those electrons more tightly. In number 16, we have to classify each of the following compounds as either ionic or covalent. So let's remind ourselves where the metals, nonmetals, and metalloids are located on the periodic table. Titanium and chlorine would be an example of a metal and a nonmetal, so that is an ionic compound. With nitrogen and fluorine, since those are both nonmetals, that's a covalent compound. With carbon and oxygen, again, those are both nonmetals, so covalent. And with iron and bromine, that's a metal and a nonmetal, therefore that would be an ionic compound. In number 17, we know that calcium reacts with sulfur to form calcium sulfide. Calcium is a metal, sulfur is a nonmetal. So when forming an ion, metals tend to lose electrons, forming positive ions or cations. Nonmetals tend to gain electrons, forming negative ions or anions. In this situation, the electrons were transferred to form an ionic bond. They were transferred from the calcium to the sulfur. In terms of the ion, calcium has a charge of 2+, sulfur has a charge of 2-, but they each have 18 electrons. They're not the same size. Calcium still has 20 protons, whereas sulfur has only 16 protons. Therefore, the calcium ion would be smaller, and the sulfur ion would be larger. So, calcium is the smaller circles because both ions are isoelectronic, and calcium has more protons. Number 19 is talking about these substances, C6H12O6, which is a form of sugar, this is glucose, and sodium chloride. Are they conductors of electricity in various forms? Well, we remember from a demonstration I did that when you dissolve sugar, whether that's glucose or sucrose in water, it doesn't matter, the covalent sugar molecules do not form ions. So it is a non-electrolyte. It does not conduct electricity because there are no ions in solution. When sodium chloride is dissolved in water, it does conduct electricity because there are ions. So the correct answer to this question is either C or D, because sugar is a non-electrolyte and aqueous sodium chloride is an electrolyte. So what about solid sodium chloride? You may remember I showed you a demonstration video in which they took solid sodium chloride and first proved that it was a non-electrolyte, and then after they melted the salt, it was able to conduct electricity. So the ions in solid sodium chloride are rigid and locked in that crystal lattice, and they are not able to be free and moving around, so they do not conduct electricity. Correct answer is D. Solid sodium chloride is a non-electrolyte, whereas aqueous sodium chloride does conduct electricity. In number 20, we have to fill in the missing information in the table below. Remember that all of the ions in group 1 will be +1, group 2 +2, group 13 +3, group 15 -3, group 16 -2, group 17 halogens -1. So based on the location of these elements in the periodic table, aluminum's +3, magnesium is +2, potassium is +1, nickel is a transition metal, but the Roman numeral tells us that nickel has a charge of +2 in this case. Nitrogen's -3, oxygen's -2, sulfur is also -2, and chlorine is -1. So for aluminum nitride, we do not have to use the crisscross rule, and the formula is simply ALN. For magnesium oxide, again, no crisscross rule, and the formula is MgO. With potassium sulfide, yes, you have to use the crisscross rule, and we get K2S. And with nickel and chlorine, yes, use the crisscross rule, and the formula is NiCl2. In number 21, we are given formulas, but we have to provide the name. And we name the cation first and the anion second. So the name of Na is sodium. Copper should have a Roman numeral since it is a transition metal, and since the charge on sulfur is -2, that means the charge on copper in this compound must be +2. So Roman numeral 2 is part of the name. Calcium is just called calcium. No Roman numeral because calcium is always +2. Iron, again, is a transition metal, and because there are 3 bromide ions, which are each worth -1, that means the total charge on iron must be +3. So Roman numeral 3 is included in the name, iron, Roman numeral 3. For the phosphorus, when it becomes a negative ion, we call it phosphide. Sulfur becomes sulfide. Fluorine becomes fluoride. And bromine becomes bromide. So these are the names of these 4 compounds. Sodium phosphide, copper Roman numeral 2 sulfide, calcium fluoride, and iron Roman numeral 3 bromide. In number 22, we have to start by counting the number of valence electrons. Then we're going to draw a skeleton for the molecule, connect the atoms with dashes. Each dash is worth 2 electrons. And then finally place dots as non-bonding pairs of electrons around any atom that needs to get a full octet. If we need to form a double or a triple bond, we might have to do that depending on how many dots we have. So starting with carbon and 2 sulfurs, that's going to contain 4 valence electrons for carbon, 6 valence electrons for each sulfur. So 4 plus 12 is 16. Our skeleton looks like this, with the carbon in the middle. We start with single bonds. Then we satisfy the octets for each of the sulfurs. So I have 4 electrons drawn so far with the 2 dashes. 6, 8, 10, 12, 14, 16. Since I have no more electrons to use, and since the carbon does not have a complete octet, I will move a pair of electrons from the sulfur to make a double bond. I have to do that on both sides so that carbon can have access to a full octet. So my final structure is going to have 2 double bonds, 1 on each side. In our next example, we have sulfur and 3 oxygens. Each atom has 6 valence electrons. That's a total of 24 electrons altogether. The skeleton puts sulfur in the middle, bonded to 3 oxygens. So we start with single bonds. I've used up 6 electrons so far with those 3 dashes. So 8, 10, 12, 14, 16, 18, 20, 22, 24. This satisfies the octets for all of the atoms except sulfur. I have to make 1 double bond, so I'll take a pair of electrons off of one of the oxygens and make a double bond. And you could have made that double bond in any of those 3 positions. For the last molecule in this set, we have silicon, which has 4 valence electrons. Fluorine has 7, so 28. 7 times 4 is 28, plus 4 is 32 altogether. Here's our skeleton. We now have drawn single bonds. That's 8 electrons so far. 10, 12, 14, 16, 18, 20. 22, 24, 26, 28, 30, 32. Everyone has a full octet. There's no reason to make any double bonds. That molecule is complete. In number 23, we're going to fill in the missing information in the table. Starting with the cation, aluminum has a charge of +3. Copper has a Roman numeral 2, so +2. Zinc, there's no Roman numeral, but we should remember that zinc is always +2. And ammonium is a polyatomic ion, which we learned from that song. Ammonium is NH4 + 1. For the anion, hydroxide is a polyatomic ion, OH - 1. Chlorate is also a polyatomic ion, ClO3 - 1. Carbonate is CO3. Its charge is -2. Nitrate is NO3. Its charge is -1. So for the crisscross rule, yes, and we get aluminum hydroxide with parentheses around the OH. Copper chlorate, yes, we have parentheses around the ClO3. Zinc and carbonate, they balance out, so no crisscross rule is needed. And the same with ammonium and nitrate, no crisscross rule is needed. For the next row of this table, we have potassium, which is +1. Lead is Pb, and the charge is +2 because the Roman numeral tells us that. And again, zinc is always +2. Chromate is a polyatomic ion, CrO4. Its charge is -2. Sulfate is SO4. Its charge is also -2. And phosphate is PO4. Its charge is -3. So we have to use the crisscross rule with potassium chromate, K2CrO4. No crisscross rule needed for the lead sulfate, PbSO4. And we crisscross with zinc and sulfate. So we end up with Zn3, parentheses around the PO4, and a 2 on the outside. All right, in number 24, we have some more Lewis electron dot structures to draw. For carbon, that's 4 valence electrons. Each oxygen would be 6. That's 10 altogether. And the 2 chlorines each have 7. So 10 plus 14 is 24. We start with singles. That's 6 electrons so far. 8, 10, 12, 14, 16, 18, 20, 22, and 24. It is more likely that oxygen forms a double bond than chlorine. So let's go ahead and make the double bond by taking a pair of electrons off the oxygen and making a double bond. Now every atom has a complete octet. Our next example, we have 3 carbons. So 3 times 4 is 12. We have 2 hydrogens with 1 electron each, so that's 14. And then we have 2 halogens, each of which have 7. So 14 plus 14 is 28. We'll start with single bonds. That's 12 electrons I've used so far in drawing those 6 dashes. So 14, 16, 18. The hydrogens are fine the way they are. 20, 22, 24. I have only 4 more electrons left. 26 and 28. That's not going to be enough to satisfy all of the carbons. That poor carbon in the middle does not have an octet unless we move a couple of pairs of electrons to make a triple bond. So that will satisfy the octet rule, and that molecule is now complete. In our third example here on this particular row, we have 2 bromines. Each have 7. That's 14. Each sulfur has 6. So 14 plus 12 is 26. We'll start with single bonds. I've already used up 6 electrons so far. 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. Every atom has an octet. There's no need to make any double or triple bonds. That molecule is complete. All right, our next row of this table, we have hydrogen plus carbon plus nitrogen. That's 1 plus 4 plus 5. That's 10 electrons altogether. We'll draw single bonds to start. I've used up 4 electrons so far. 6, 8, 10. But the carbon doesn't have a complete octet unless we move electrons to make a triple bond. And once we do that, every atom has a complete octet, and that molecule is done. Phosphorus has 5 valence electrons. Each chlorine has 7. There's 3 of them. So 5 plus 21 is 26. Here is our skeleton. We'll start with single bonds. That's 6 electrons so far. 8, 10, 12, 14, 16, 18, 20, 22, 24. There's no reason to make a double bond because we have 2 more electrons, and now every atom has a complete octet, so that molecule is done. Sulfur is 6, fluorine is 7. 6 plus 14 is 20. Here's our skeleton. Let's connect with single bonds. That's 4 electrons. 6, 8, 10, 12, 14, 16, 18, 20. No reason to make double bonds. Every atom has a full octet. That molecule is complete. All right, that wraps up the practice quiz on the periodic table and chemical bonding. I hope that those answers and explanations were helpful. Thanks for watching, and good luck studying.